Okay, welcome to Chapter 4, Determinants. Let's take a look at the Section 4.1 notes, areas, volumes, and cross products. So the plan in this section is to motivate something called the determinant of a matrix. We'll take determinants of 2x2 and 3x3 matrices in this section. We'll do general determinants soon. And this is, some of the algebra in this section is fairly clunky, but the plan is to motivate this method of taking determinants. And we're really not that interested in taking determinants for the sake of taking determinants. We're really interested in some other stuff. One of those other things will be eigenvalues, and that's the topic of Chapter 5. And eigenvalues are computed using determinants, so determinants are a necessary evil. So the title of the section is Areas, Volumes, and Cross Products. So again, it's motivation for this manipulation that we'll do to certain square matrices. Determinants play a central role in matrix theory. Historically, determinants even are a concept that predates that of the concept of a matrix. And there's a little story in the book on page 251. But where this stuff comes from is systems of equations. Determinants can be used to solve systems of equations. We'll mention, maybe in passing, how that's done. We've got a pretty robust way of solving systems of equations, and it's way more efficient. Gauss-Jordan elimination is way more efficient than using determinants, but they play a historical role in systems of equations. In this section, we're motivating the study of determinants by considering areas of parallelograms in R2 and volumes of boxes in R3. They're sometimes called parallelepipeds. That's sort of a three-dimensional analog to a parallelogram. And along the way, we'll define the cross product of two vectors in R3. Maybe you've seen cross product before, either in a physics class or Calculus 3. You'll encounter them in Calculus 3. They have some really useful physical properties. So away we go. Area of a parallelogram. So here we've got an image of two vectors, A and B, in blue. Let's make them a little bigger. And these two vectors determine a parallelogram in light blue. So matrix A in standard position, matrix B in standard position, that is with their tails at the origin of a coordinate system. We've introduced an angle theta between A and B, and we want to find the area of this blue shaded region. Area is, well, it's base times height. It's not a rectangle, but it's still base times height. If you think about it, we could cut off this little triangle on the left-hand end and translate it over here to the right-hand end in a parallelogram. That would produce a rectangle. Its base would be, actually this distance here would be the magnitude of vector A, and its height would be this parameter lowercase h here. So we need to find that lowercase h. But we're looking at area of the parallelogram is base times height. The base is the magnitude of vector A. The height, well, we got a little right triangle here. Angle theta has as its opposite a side of length h, and as its hypotenuse, a side of length magnitude of b. So the sine of theta is h over the magnitude of b, or h is the magnitude of b times the sine of theta. The height is the magnitude of b times the sine of theta. It's just opposite hypotenuse trig function stuff. So base times height, base is magnitude of A, height we just saw is magnitude of B times the sine of theta. For reasons to be made less transparent shortly, let's take that sine of theta and write it as 1 minus cosine square root of, what's the Pythagorean theorem? Sine squared plus cosine squared equals 1. Provided the sine is positive, then we can write the relationship between the sine theta and the cosine theta is given here. we're looking at an angle between vectors, and it should seem fairly reasonable that that angle would be measured between 0 radians and maybe pi radians, in which case the sine function is non-negative, and we're good to go on this representation. So for some reason, we want to introduce a cosine of an angle between vectors. We dealt with a cosine of angles between vectors before when we dealt with dot products. So that's the real motivation for introducing the cosine stuff. All right, let's square both sides. We've represented the area that we're looking for as a capital A. Of course, that'll be non-negative. We square both sides. We'll get a squared equals norm of a squared, norm of b squared. We get rid of that square root. We get a 1 minus cosine squared theta. Distributing, we get the area squared is norm of a squared, norm of b squared, minus norm of a squared, norm of b squared, cosine squared theta. If you'll recall from chapter 1, I think it was, the dot product between two vectors was the product of the magnitudes of those vectors times the cosine of the angle between them. Or maybe this sounds more familiar. The cosine of theta, the angle between vectors A and B, was the dot product of A and B divided by the magnitude of A times the magnitude of B. And we've got all these squares because we're dealing not with cosine theta, but cosine squared theta. Anywho, we can rewrite this last expression as a dot product. So we can express that area squared as magnitude of A squared times magnitude of B squared minus the dot product of A and B squared. Well, we got our reasons. We want to write those vectors in terms of components. If vector A has components A1 and A2, remember all this was happening in the Cartesian plane, so these are vectors from R2. And vector B has components B1 and B2, then A squared can be written as, trust me, it skips some arithmetic here, but if we'll calculate the magnitude of A squared, that'd be A1 squared plus A2 squared, magnitude of B squared, B1 squared plus B2 squared. Don't have the square roots because of the squarings on those norms. A dot B squared would be A1 times B1 plus A2 times B2, quantity squared, because that's squared. You follow your nose on the arithmetic, that will simplify down to the following. We'll get A squared, the area squared is the quantity A1 B1 minus A2 B1, quantity squared. If we take square roots of both sides, the square root of A squared is A. Well, okay, it's the absolute value of A. It's an area, so it's not negative, and I don't need the absolute values there. Take the square root of the right-hand side, A1 B1 minus A2 B1. What was that? A1 B2 minus A2 B1. Quantity squared, square root of, that will produce an absolute value, because I don't know whether that's positive or negative. So we'll put an absolute value on there, and we can express the area of this parallelogram determined by vectors A and B in terms of the components of vectors A and B as given here. Okay, that's barely vector calculus at all, other than the notation and maybe the fact we use dot products to find cosines. With that as motivation, we're going to define the determinant of a 2x2 matrix as follows. We have a matrix A, the first row of which is A1, A2. The second row is B1, B2. Define the determinant of A as determinant of A is A1, B2 minus A2, B1. It's also sometimes denoted with these long bars. These are not absolute values. These are determinant bars. It means take the determinant of the array or the matrix between the two horizontal bars. And the way this is computed is we take A1 times B2 and multiply, and then swing around and subtract A2 times B1. So it follows this little path in terms of how the computation's done. You can argue with it. It's a definition. I'm trying to motivate that definition. That's the plan here. And, whoa, that's the same thing we had up here. This determinant of this little matrix, A1, B2 minus A2, B1, why the absolute value of that is the area of the parallelogram determined by vectors A and vector B. To date, we never put vectors in a matrix as anything but columns. We did it with standard matrix representation. We did it when we were looking for linear independence, when we were looking for basis of a span of vectors. And vectors, they always went in a matrix as columns. Here, so this is an exception to that pattern. Here, we've got A1, A2 as the first row. Those are the components of vector A. B1, B2 is the second row. Those are the components of vector B. So if you want to find, and you're going to want to find it, the area of a parallelogram is given on the previous page in the picture. You want the area of this parallelogram determined by vector A and vector B, and you're given vector A and you're given vector B. You take the components of A and the components of B and enter them in a 2x2 matrix as rows. Components of vectors go into this matrix as rows. That's a first for us. And then you take the determinant. Ooh, and then you'll have to take an absolute value. It's an area, of course, it should be non-negative. So let's illustrate exactly that in 4.1, number 20. Okay, so the instructions are: find the area of the parallelogram with vertex at the origin and with vectors -i plus 4j and 2i plus 3j in standard position as edges. Okay, we don't really need to draw a picture. That picture we had before schematically is good enough. So what we'll do is take these vectors, write them in the little square bracket notation. So we can easily pick the components off. So -i plus 4j is a vector with components -1, 4. Let's call that A1 and A2. The other vector, 2i plus 3j, has components 2 and 3. Let's call those B1 and B2. So the area of the parallelogram should be, our previous conversation, the absolute value, little horizontal lines do mean absolute value here, the absolute value of the determinant of matrix A, where matrix A has the components of vector A in the first row and the components of vector B in the second row. So we'll put the -1, 4 and the 2, 3 in as rows of matrix A. All we got to do is take the absolute value of the determinant. Okay, so absolute value of the determinant of matrix A, that'd be the absolute value. It ain't my fault, but this is a notation we're stuck with. The outer little horizontal lines mean absolute value. The inner little horizontal lines mean take the determinant of the array inside, the matrix inside. So we'll take the absolute value of the determinant. Determinant of this 2x2 matrix would be -1 times 3 minus 4 times 2. -1 times 3 minus 4 times 2. That's -3 minus 8. It'll give us -11. We take the absolute value of that. We get +11. The area of that parallelogram is +11. This is kind of weak motivation, but that's a whole bunch easier than plotting those two vectors in R2 and then trying to take the resulting image and cut it up into pieces where you get a rectangle. So that's effectively what we've done underneath all of this stuff. So there's using determinants to determine areas of parallelograms in R2. We've only got things set up in 2 dimensions. How about this? Find the area of the triangle with vertices 3, -4, 1, 1, and 5, 7. Okay, well, we're still in R2. These are points in the Cartesian plane. Here they are in a reasonably good scale drawing. And in yellow is the triangle we're looking for the area of that triangle. It don't look like no right triangle, so finding the area could be a challenge. And we ain't equipped to find areas of triangles. We're equipped to find areas of parallelograms using vectors. So tell you what, let's introduce a vector A from point 1, 1 to point 3, negative 4. So vector A will point along this edge of the triangle. Let's let vector B be from the point 1, 1 to the point 5, 7. So vector B will point along this side of the triangle. So we'll have two vectors. Well, they'll determine a parallelogram, and I think we can relate the area of that parallelogram and the area of this triangle. So with A as a vector from 1, 1 to 3, 4, old story here, the components of vector A are 3, minus 1 and negative 4, minus 1. That is 2, negative 5. The components of vector B from 1, 1 to 5, 7 would be 5, minus 1, 7, minus 1, giving us a vector B of 4, 6. So let's take those vectors. Here they are, A and B, drawn not in standard position, but drawn along the edges of the desired triangle, the yellow triangle. But now vector A and vector B, they determine a parallelogram. And what we get is a kind of a flipped around mirror image of a triangle, the yellow triangle over here on the right. It's the other half of a parallelogram. Well, we can find the area of the whole parallelogram using determinants. We'll just take that and cut it in half, and that'll give us the area of the yellow triangle. Okay, so the area of the triangle would be 1/2 the absolute value of the determinant of matrix A, where matrix A has those components of vectors A and vector A and vector B as its rows. We had, I guess, vector A had components 2, negative 5, vector B had components 4, 6, so that'll produce this matrix. We want 1/2 the absolute value of the determinant of that matrix. That'd be 1/2 absolute value of the determinant of the matrix. For the determinant, we'd have 2 times 6 minus negative 5 times 4. Be very, very careful in the notes. I've laid all the computations out. It'd be easy enough to lose a negative sign in all of this. But that'll produce this. 2 times 6 is 12, minus negative 5 times 4, be 12 plus 20, be 32. Absolute value of 32 is 32. Divide by 2 for the 1/2 out front. 32 is the area of the whole parallelogram. Cut it in half. The area of the desired triangle is 16. Back to the notes. Okay. And shifting gears a little bit, going into 3 dimensions. Consider 2 vectors, B and C, and R3. So let vector B have components B1, B2, B3. Let vector C have components C1, C2, C3. And define, you can't argue with them because it's a definition, but we're defining the cross product of B and C using determinants. We're defining B cross C to be the vector with first component, there's an I here, the determinant of the matrix B2, B3, C2, C3. Second component, there's a J vector here, the negative of the determinant of B1, B3, C1, C3. And third component, there's a K here, the determinant of B1, B2, C1, C2. All right, well, there's your definition of cross product. So you're looking for patterns here. One of the patterns is there's no subscripts of 1 in the first one, there's no subscripts of 2 in the second one, and there's no subscripts of 3 in the third one. We'll have a more tangible way of remembering this shortly. But first off, notice what this does, this is the first time we've done this, is it takes 2 vectors from R3 and produces from them, through this process of cross product, another vector in R3. So we've multiplied two vectors together and got a vector. We've never done that before. We multiplied two vectors in Rn together with a dot product, but that didn't give a vector, that gave a scalar. Dot product, sometimes called scalar product, sometimes called inner product as well. So there's the cross product of vectors B and C. Okay, well, it turns out that this is a very useful thing to do to vectors. The first claim is that when we take a dot product of vectors B and C, the vector that is produced is perpendicular to both vector B and vector C. We could go through, how do you show orthogonality? Dot product should be 0. So we could take the dot product of vector B with B cross C, you get 0 out. They are orthogonal, perpendicular. Same with C. Take vector C, dot it with B cross C, you'll get the 0 scalar out. So B and C are both perpendicular to B cross C. We can compute, so here's a little symbolic way, and this is foreshadowing determinants of 3x3 matrices. Right now it's just a little picture to help you remember how to take a cross product of two vectors. We could compute the cross product of B and C as follows. We're going to put I, J, and K in the first row of this matrix. Now this is messed up because matrices, as far as we're concerned, they got numbers in them. They don't have vectors in them. Well, this is the only time we'll see something like this. And again, this is motivation for something to come in the near future. So we'll put I, J, K in the first row of a matrix, the components of vector B in the second row, the components of vector C in the third row. Order is going to matter. We're taking B cross C. It'll turn out, surprisingly, B cross C and C cross B are not the same. This is not a commutative operation. So put things in order. And we're interpreting this as the determinant of the matrix B2, B3, C2, C3 times I minus the determinant of B1, B3, C1, C3 times J plus the determinant of B1, B2, C1, C2 times K. Same as the definition we had above, but we'll put some geometry on this shortly. What we're doing, so I can't highlight things quite the way I want. What we're doing is taking first the I vector and eliminating the column and the row containing that I vector mentally cross it off when we have an algorithms, how they'll describe it. And then we're looking at what's left. And it's this little 2x2 submatrix, minor matrix, it'll be called at some point. B2, B3, C2, C3. So we've got the I times the determinant of that little minor matrix. And I told you there wasn't anything with a subscript of 1 in the first one. In the second one, we're eliminating, conceptually, the row and column containing the J. That'll leave us with B1, B3, C1, C3, and that's the entries here. There's the J. Not a typo. There's a negative there for reasons to be made apparent later. And similarly in the K position, we'll eliminate the row and column containing K. It leaves this. Now you're good to go because you know how to take determinants of 2x2 matrices. So you plow through all of that, and that will allow you computationally to find a cross product of two vectors. And there ain't a quicker way than this. This is as efficient as it can be in terms of taking cross products. Now we commented above that the cross product was perpendicular to both vector B and vector C. So here's a little image, figure 4.3 out of the book. And these cross products represent physical things, in particular, angular momentum is represented by a cross product. Gyroscopes behave based on some angular momentum stuff. A bicycle is easier to balance when it's in motion than when it's stationary because of angular momentum. And this angular momentum is defined in terms of a type of cross product. We know geometrically, or we could easily confirm, that the cross product vector B cross C is perpendicular to both vector B and vector C. Got the little perpendicular symbols here indicating that that cross product is perpendicular to both of those. Being a vector in R3, it'd be reasonable to ask about its magnitude and direction. We'll get there on magnitude. Right now, we're trying to resolve direction. So what they're saying is, hey, here's a vector that's perpendicular to both B and C. Yeah, I could reverse the direction of it and it'd still be perpendicular to both B and C. So why pick this direction over the opposite direction? This is geometrically how cross products behave. And here's how you think about it more tangibly and geometrically. Pops up a lot in electricity and magnetism as well. And working problems, you need to be conscious of directions of vectors in 3 dimensions. And the way you determine directions of cross products is the right-hand rule. So what we're going to do, as you see in the image, is take the fingers of your right hand. Take the fingers of your right hand. We're taking B cross C. Curl the fingers of your right hand from vector B around to vector C. The direction of your thumb then will determine the direction of B cross C. So you take the direction, take the fingers of your right hand and curl, say, from B to C, and your thumb points up. That's the direction of B cross C. Notice I'm curling around in this direction. If I curl the fingers of my left hand in the same direction, then my thumb points down. So there's a handedness to it. Some pragmatic information. You've got trying to take a screw out of a socket in the wall or something. What you'll do is you go up to it with a screwdriver, then you grab the screwdriver with your right hand. You want that coming out of the wall, grab the screwdriver with your right hand, rotate this way. Your thumb will indicate the direction in which the screw will move if you turn the screwdriver according to a right hand rule. You're putting it into the wall, grab the screwdriver, rotate it this way, and that'll take the screw into the wall, unless you found some perverse left-handed screws. They're out there. But primarily screws are right-hand rule screws. DNA curls, it has a direction to it. DNA has a right-handedness to it as well. But there's some geometric properties of cross products of vectors. This offer only valid in 3 dimensions, so we're only talking about vectors in R3. We have the equipment to compute a cross product, so let's go to Beamer files, and they give us 2 vectors and they ask us to find a cross product. These guys, they've changed it to vector A and vector B, but whatever, just preserve the order and we're good. Okay, they give us vector A is I minus j plus k. Okay, let's write it in terms of components more explicitly with the square brackets as 1, negative 1, 1. Vector B is 3i minus 2j plus 7, so its components are 3, negative 2, 7, 3, negative 2, 7. We'll put those into a 3 by 3 matrix, if you like, with the ijk's, or just take the original definition we had. It's a little bit easier. Maybe I introduce that 3 by 3 matrix symbolically that represents determinants, or I'm sorry, cross products. They will be determinants, as we'll see shortly, for 3 by 3 matrices, but that's not formally defined yet. So we'll go through and plug the numbers in according to this formula. So we need A2, A3, negative 1, 1, negative 1, 1. B2, B3, negative 2, 7, negative 2, 7. Doesn't include the ones with a subscript of 1, and so forth. So I won't bore you with the details, but we follow the formulas and produce this. Be very, very careful. There's a negative sign here. Again, not a typo, to be explained not too distant future. Okay, so we'll take those determinants. This first one will have -1 times 7 minus 1 times -2. That'll be times vector I, right? -1 times 7 minus 1 times -2. Think of it as cycling around in a sense. I, 1 times 7 minus 1 times 3, 1 times 7 minus 1 times 3 times j. Don't forget the negative out front in that middle component. And then similarly for the k, and that produces the vector -5, -4, 1. What's that mean? Not a whole lot just yet. It's a vector that's perpendicular to both of these. If I could visualize vector A and vector B, I could tell what direction this is with the right hand thing. Curl your fingers from A to B, and then your thumb will point in the direction of this vector A cross B. But beyond that, we don't have a lot of information in exactly what this tells us just yet. Back to the notes. All right, next we'll define the determinant of a 3x3 matrix, and this will be intimately related to the way we compute cross products. But let me cut this video here and we'll go to a second video for this section and finish up the section.